Welcome to the new era of video creation with Bayozi. This is our new series on teaching deep learning. Today we will discuss the feature extraction. Here are the contents. Feature extraction is the process of transforming raw input data, typically pixel values from an image, into a more compact and meaningful representation that captures the key characteristics of the image. These extracted features are used for tasks like object detection, image classification, and scene understanding. In computer vision, feature extraction can be divided into two broad categories: handcrafted features and learned features. Handcrafted features were manually designed based on domain knowledge, whereas learned features are automatically discovered through algorithms, particularly deep learning techniques like convolutional neural networks, CNNs. Feature extraction plays a crucial role in simplifying the complexity of image data while retaining essential information, making it easier for machine learning algorithms to process and understand. Over the next few slides, we'll dive deeper into the various techniques of feature extraction, from traditional methods to deep learning-based approaches. Before the rise of deep learning, handcrafted features were the backbone of feature extraction in computer vision. These features were designed based on human intuition and understanding of image properties. For example, features like edges, corners, and textures are essential for understanding the content of an image. Handcrafted features include methods like SIFT, scale invariant feature transform, HOG, histogram of oriented gradients, and SURF, speeded up robust features. SIFT extracts distinctive key points in images by detecting stable regions of interest that are invariant to scale, rotation, and affine transformations. These key points are used to match images and recognize objects. HOG focuses on capturing the gradient orientations in an image. It's particularly effective for detecting objects like humans in images by representing local shapes and structures. SURF is a faster alternative to SIFT that also detects distinctive key points, and it is invariant to scaling and rotation. Handcrafted features have the advantage of being interpretable and easy to implement. However, they often fail to capture complex patterns in images, which is why more advanced learned approaches are increasingly popular. The shift to deep learning in computer vision brought about a fundamental change in how features are extracted. Rather than relying on manually engineered features, deep learning models, especially convolutional neural networks, CNNs, are able to learn the most relevant features directly from data. This shift allows for the extraction of complex and hierarchical patterns in images, such as edges, textures, shapes, and even high-level concepts like objects or scenes. Unlike handcrafted features, learned features can automatically adapt to different types of input data and tasks, improving accuracy and generalization. In CNNs, the network learns low-level features like edges in the initial layers, and more abstract, complex features like object parts or whole objects in deeper layers. This ability to learn features directly from data is a major advantage over traditional handcrafted methods. At the heart of feature extraction in modern computer vision are convolutional neural networks, CNNs. CNNs are designed to automatically learn and extract features from images by applying convolutional layers. Each convolutional layer applies a set of filters, or kernels, to the image to detect local patterns such as edges, textures, and simple shapes. These filters slide across the image, or feature map, performing the convolution operation at each position. The output is a new image, or feature map, that highlights the presence of the learned pattern. With each successive layer in the network, the model learns more abstract features. For example, early layers might detect simple edges, while later layers may detect parts of objects like eyes or wheels, eventually learning to identify entire objects like faces or cars. This hierarchical structure allows CNNs to automatically extract relevant features from data, eliminating the need for manual feature engineering. When a filter is applied to an image through a convolutional layer, the result is a feature map. A feature map is a new representation of the input image that highlights specific patterns or features detected by the filter. These patterns can include edges, gradients, textures, and even more complex features as we move deeper into the network. Multiple filters are applied at each convolutional layer, and each filter learns to detect a different pattern or feature. For instance, one filter might detect horizontal edges, while another might detect vertical edges or corners. By using a combination of filters, CNNs can learn a wide variety of features that capture the important characteristics of an image. Feature maps provide a compact and informative representation of the image, which can then be passed through subsequent layers of the network to detect higher-level structures. Once the features are extracted through convolution, pooling layers are applied to reduce the spatial dimensions of the feature maps. Pooling helps downsample the feature maps, retaining only the most important information while discarding redundant details. The most common pooling methods are max pooling and average pooling. Max pooling takes the maximum value from a set of neighboring pixels, usually in a 2x2 region, which helps retain the most dominant features while reducing the size of the feature map. Average pooling takes the average value from the neighboring pixels, which is more sensitive to the overall distribution of values rather than the dominant one. Pooling helps introduce translation invariance, meaning that slight shifts in the position of features will not drastically affect the feature maps. It also reduces the computational cost by making the network more compact and helps in preventing overfitting by abstracting away unnecessary details. Feature extraction plays a crucial role in object detection, where the task is to both classify and localize objects within an image. The network first extracts features from the image and then uses those features to predict bounding boxes around objects and assign class labels. Modern object detection systems use CNNs to extract features from images, which are then processed to detect and localize multiple objects. Some well-known models that perform feature extraction for object detection include RCNN, region-based CNNs that first generate potential object regions using selective search and then classify them using CNNs. YOLO, you only look once. A more efficient approach that predicts both bounding boxes and class labels in a single forward pass of the network, making it faster and more suitable for real-time applications. SSD, single-shot multi-box detector, a fast object detection framework that predicts multiple bounding boxes and class labels in a single pass through the network. Object detection is widely used in applications like autonomous driving, security surveillance, and robotics, where extracting meaningful features and accurately detecting objects in images is critical. Semantic segmentation involves classifying every pixel in an image into one of several predefined categories. Unlike object detection, which localizes objects using bounding boxes, semantic segmentation requires more detailed information, with each pixel labeled according to its class. Feature extraction plays an important role in semantic segmentation by enabling the network to capture spatial and contextual information for every pixel in the image. CNNs, particularly those with fully convolutional architectures, FCNs, are used to extract features that enable the network to make pixel-wise predictions. FCNs remove the fully connected layers from traditional CNNs, allowing for end-to-end pixel-level prediction. Popular models for semantic segmentation include UNet, a model specifically designed for medical image segmentation. It has a symmetric encoder-decoder structure with skip connections to retain spatial details. DeepLab, a family of models that utilizes dilated convolutions to capture multi-scale context for better segmentation performance. Semantic segmentation has applications in medical imaging, where precise delineation of organs or tumors is required, and autonomous driving, where road regions, vehicles, and pedestrians need to be segmented. Transfer learning is a technique where a pre-trained model, trained on a large dataset like ImageNet, is used as a feature extractor for a new task. The idea is to leverage the knowledge the model has learned from a large dataset and apply it to a new, potentially smaller dataset. This approach is particularly useful in computer vision, where obtaining labeled data can be expensive and time-consuming. By using a pre-trained CNN model, such as VGGNet, ResNet, or Inception, as a feature extractor, you can fine-tune the model on a new dataset using fewer resources and time. Transfer learning is widely used in many applications, including object detection, classification, and segmentation, especially when the available labeled data is limited. Video analysis presents unique challenges because, in addition to spatial features, temporal features, movement between frames, need to be extracted. For this, CNNs can be extended to 3D, where the third dimension represents time. 3D convolutions allow the network to capture spatiotemporal features from video frames, learning patterns that change over time. Another approach is to combine CNNs with recurrent neural networks, RNNs. While CNNs are used to extract spatial features from individual frames, RNNs are used to capture the temporal dependencies between frames. The combination of these models makes it possible to analyze video for tasks such as action recognition, object tracking, and even activity prediction. In face recognition, the goal is to identify or verify individuals based on their facial features. This task requires extracting distinct features from the face, such as the eyes, nose, mouth, and overall facial geometry. CNN-based models like FaceNet and VGG-Face are designed to extract these distinctive features from images of faces. These models can generate embeddings, which are compact representations of the face that can be used to compare and match different faces. By extracting facial features, CNNs can achieve high accuracy in recognizing and verifying individuals, even under variations in lighting, pose, or expression. Applications of face recognition include security systems, social media platforms, and access control systems. Despite the advancements in feature extraction, several challenges remain. Variations in lighting, pose, and scale can make feature extraction difficult. For instance, an object may look very different when viewed from a different angle or under different lighting conditions. Traditional handcrafted features like SIFT and HOG can struggle with these variations, and even CNNs can face challenges unless properly trained. Furthermore, complex backgrounds and noise in the images can interfere with the ability of the model to extract relevant features. Background clutter may distract the model, especially in real-time or unconstrained environments. Finally, limited labeled data remains a significant challenge, particularly for specialized tasks. Data augmentation and transfer learning can help, but some domains still face difficulties in obtaining sufficient labeled datasets. Feature selection involves choosing a subset of relevant features from the original set of extracted features, while dimensionality reduction techniques aim to reduce the number of features, maintaining only the most informative ones. Methods like principal component analysis, PCA, are commonly used to transform high-dimensional feature sets into lower-dimensional ones, capturing the most important information. TSNE is another technique often used for visualization, reducing dimensionality while preserving the pairwise relationships between features. Dimensionality reduction not only helps in improving computational efficiency, but also can mitigate the curse of dimensionality, leading to more robust and interpretable models. Feature extraction has a wide range of real-world applications across various industries. Autonomous driving, feature extraction is used for detecting pedestrians, vehicles, and traffic signs, helping self-driving cars understand their environment. Facial recognition, used for verifying identities in security systems or for automatically tagging photos in social media platforms. Medical imaging. Feature extraction is critical for identifying tumors, organs, and abnormalities in medical scans like MRIs or CT scans. Image search engines. Feature extraction enables content-based image retrieval, where users can search for images based on their visual similarity. These applications benefit from the power of feature extraction, allowing systems to understand and process visual data efficiently. Feature extraction remains a foundational task in computer vision, whether using traditional handcrafted methods or modern deep learning-based techniques. While deep learning has dramatically improved the efficiency and accuracy of feature extraction, challenges such as robustness to variations and the need for large datasets persist. Research in feature extraction continues to evolve, focusing on improving efficiency, scalability, and accuracy across diverse applications. Additionally, we are seeing the integration of feature extraction across different data modalities, such as combining vision with text or audio to create more holistic AI systems. The future of feature extraction will continue to push the boundaries of what's possible in understanding visual data, and the developments in this area will have a significant impact on the progression of AI technologies in many fields.